Welcome back to the channel. Today we're diving into one of the most mysterious and powerful concepts in all of physics, the wave function. If you've ever wondered how quantum mechanics describes reality, or what Schrödinger's cat has to do with waves, this is the video for you. We'll go deep, but don't worry, I'll explain everything step by step. Grab a coffee, relax, and let's journey into the quantum world. So, what exactly is a wave function? In quantum mechanics, the wave function is the mathematical core that describes everything we can know about a quantum system, like an electron, a photon, or even an atom. It's usually represented by the Greek letter psi. The wave function isn't a physical thing you can touch or see. It's more like a probability cloud. It tells us where a particle might be, how fast it might be moving, or what state it might be in. But here's the twist: psi itself doesn't give us probabilities directly. Instead, we take the square of the wave function's magnitude, psi superscript 2, and that gives us the probability of finding the particle in a particular state. Think of psi like a recipe, full of ingredients you need to cook up reality. But it only becomes useful once you square it. Now comes the philosophical bit: wave function collapse. Before a measurement, the wave function represents many possible outcomes. But when we measure something, say, the position of an electron, the wave function suddenly collapses to a single value. Why does this happen? Honestly, we don't fully know. This is the famous measurement problem in quantum mechanics. Does the wave function really collapse? Or is collapse just what happens when we update our knowledge? Some interpretations, like the Copenhagen interpretation, say the collapse is real. Others, like the many worlds interpretation, say collapse doesn't happen. Instead, every possible outcome happens in a branching multiverse. It's one of the most mysterious parts of physics. Two key features of the wave function are superposition, entanglement. Superposition means a system can be in multiple states at once, like Schrödinger's cat, alive and dead until observed. The wave function doesn't choose until you look. Entanglement is when two particles share a single wave function. Measure one, and the other reacts instantly, even across galaxies. Einstein called this spooky action at a distance, but experiments have confirmed it. Entangled wave functions are real, and they defy classical logic. Real-world applications. You might be thinking, this is cool, but does the wave function have any practical use? Oh yes. Quantum computing relies on qubits, systems in superpositions, governed by wave functions. Quantum cryptography uses entanglement and wave functions to create ultra-secure communication. MRI machines work thanks to quantum spin states, again described by wave functions. Semiconductors and transistors, the heart of all electronics, depend on quantum tunneling and behavior described by wave functions. The wave function isn't just abstract math. It powers your phone, your computer, and future tech. Visualizing the wave function. Now let's imagine the wave function. For a single particle in one dimension, psi x might look like a wavy line. Peaks and troughs, just like water waves. The higher the peak, the higher the probability of finding the particle there. In quantum wells or atoms, wave functions can look like standing waves, stationary patterns that fit certain energy levels. In 3D, psi becomes more complex but beautiful. Think orbital clouds around atoms. These aren't electrons orbiting like planets, they're probability clouds shaped by the wave function. We mentioned the Copenhagen and many worlds interpretations earlier. Let's dig a bit deeper. Copenhagen interpretation. The wave function is just a tool. It collapses when measured. Reality is fuzzy until you look. Many worlds interpretation. All outcomes happen. The universe splits with each measurement. No collapse, just branching. Pilot wave theory, Bohmian mechanics. The particle is real and guided by the wave function, which acts like an invisible pilot. Objective collapse theories. The wave function is real and collapses spontaneously, even without observation. Each theory has strengths and challenges, but they all agree. The wave function is central to how we understand quantum reality. Limitations and open questions. Even though the wave function is powerful, it's not perfect. For one, it doesn't include gravity. That's why we don't have a full theory of quantum gravity yet. And while we can use wave functions to describe small systems beautifully, things get really messy with large, complex systems like humans or planets, there are still deep questions like, is the wave function a real physical thing? Why does collapse happen at all? Can we one day unify it
The
with
bright
general
lines are where
relativity?
the top